Hello and welcome to our physical sciences session. My name is Temba. Today we are focusing our attention on a very exciting part of chemistry which has to do with reactions that actually take place in an aqueous solution, right? Because in nature there are many reactions that take place, and the medium in which these reactions actually take place is what is of particular interest for us today, right? Okay. So this is under the broader knowledge area of chemical change. So we'll look at solutions, but what exactly makes up a solution? It's a solvent, the substance in which a solute kind of dissolves in that. So if you have a solute and a solvent, you actually get a solution. So if a substance is dissolved in water, it gives us an aqueous type of a solution. So this is what is going to be of interest to us for today, right? Okay. Now, the thought that's going to guide our discussion for today is that have you thought about why do some chemicals actually dissolve in water? All right, because we're talking about these reactions that take place in aqueous solutions. So the big question that we want to kind of arrive, at some kind of understanding is that why do these chemicals actually dissolve in water while some they do not, right? Okay, so some of the terminology that we're going to use today are as follows. We have got the solute, okay, which is actually a substance, a solvent, which is another substance put together, giving us a solution. And then the other term is electronegativity. Speaking of terminology, this taps into our understanding in terms of recalling or remembering some things that we have been taught or we have been learning in the process. So when we talk of definitions, remember, it's either you remember or you don't, okay, because it is about remembering, which is why if a question has to do with defining a concept or a term, the idea is that you need to use the correct or the correct keywords in the correct context. So it's either 2 marks or nothing. In some cases, you'll be given a description and you have to identify the term that fits the description. So we are still defining, it's just that we're doing it backwards, right? So these are some of the terms that are very important in as far as reactions that take place in an aqueous solution. Right, so water is a very important solvent, okay? So if we say that water is a solvent, it means it has the ability to dissolve other substances, or in other words, other substances can actually be dissolved in water to give us what we would refer to as an aqueous solution. So any solution that is formed with water as a solvent is called an aqueous solution. So when we talk of an aqueous solution, it means water is the solvent in that particular solution. Because what is it that we know about a solution is that a solution consists of, a homogeneous mixture of a solute and a solvent. And remember, when we talk of a homogeneous mixture, it means if we have a sample of this solution, it means we are not therefore able to distinguish between, the particles that make up the solute and those of the solvent. So that kind of, knowledge needs to come to the fore, right? Okay, so that's very important. Now, the big question again is, why is water such a good solvent? Our bodies consist of a very huge percentage of water. It's also, if you look at many of these reactions, they actually take place in the presence of water. So water is a polar molecule. So there's a very important term that we spoke about in terms of electronegativity, right? So electronegativity is a measure, of the tendency of an atom to attract the bonding pair of electrons. So there is a bond that exists between the oxygen as well as the hydrogen atom in a water molecule. Remember, this model comes from the chemical formula H2O. So it means for every oxygen atom, there are 2 hydrogen atoms bonded, to each other. So there's a bond that exists between oxygen and hydrogen. And also, you need to realize that the oxygen has a greater electronegativity than that of hydrogen. That's why the molecule of water is polar. Why? Because where there's an oxygen atom, there's a slightly negative charge because of the high electronegativity value of oxygen. So the oxygen has a tendency to actually attract this bonding pair more than the hydrogen, which makes the hydrogen to have a slightly positive charge, which we'll refer to as a delta positive charge. Similarly, the other hydrogen atom will also actually show the very same characteristics. That's why water is considered a polar molecule. Why is it a molecule? It is because it is a covalent compound, right? So water is molecular as well as polar. So this is all about in terms of the chemistry of water as a very good solvent, right? Okay, and then also there's a strong electrostatic forces between water molecules. So there are very strong forces between water molecules. We call them intermolecular forces, okay? This means that the water molecule remains a liquid at room temperature. I think part of the reason why water becomes a very ideal, natural habitat, for aquatic animals is because it can stay a liquid, over a very wide range of temperature. That appeals, to the forces that exist actually between the water molecules. Okay, so we are actually relating the knowledge of water as a molecule to that of its application, in real life. Right, so that's very, very important. And then also, these strong electrostatic between the water molecules and particles of other substances result in dissolving. The reason why water is able to dissolve particles, of substances is because of these electrostatic forces that exist between the water. It means the forces that exist between water molecules can actually detach the particles from a crystal lattice if it was a solid. So that's why water is a good solvent, right? And then salts, which are actually solid, most of them at room temperatures, they are ionic substances because they consist of positive as well as negative ions that are pegged in a crystal lattice, okay? So the water molecules, they surround these ions and overcome the forces between these ions. That's why water is able to dissolve many salts. Not all, but many of them, they're actually soluble in water, right? Okay, now this is exactly how we would actually model what exactly happens, at a particle level when a salt dissolves in water. So the salt consists of the sodium cation, which is positive, and the chloride anion, which is negative, right? Now, what are we saying? Around the chloride ion, because of these strong electrostatic forces between the water molecules. Now, the chloride cation, which is negative, is actually surrounded by water molecules. But realize that there is a force that exists between the negative chloride anion and these hydrogen ions in the water molecules, which are positive because they are opposite in charge. And then the opposite happens with the cation of sodium. What is surrounding these water molecules are actually these molecules, and you realize that the oxygen is the one that's closer to the cation, yet on the other side is actually the hydrogen part of the water molecule. So this is exactly what happens when a salt dissolves in water. Right. Okay. So in dissolving, you'll have, for argument's sake, an ionic substance like sodium chloride. Now, because water is a very good solvent, sodium chloride is completely soluble in water. Okay. Now it then breaks down into its individual ions. So when a salt dissolves in water, the process is referred to as dissociation. Right. Okay. And then some of the salts, they don't dissolve. We have said that not all salts are actually soluble in water. Okay, these salts that do not dissolve in water, we'll describe them as insoluble salts. Okay, but there are solubility rules that are very important, and these solubility rules actually get to explain to us why some salts are insoluble. It's because the forces between the ions in the insoluble salts are stronger by comparison to those that are present between water molecules. So if the forces in water molecules are weaker than the forces between, the insoluble salt, it means those salts, they cannot dissolve in water. That's the main idea about, the solubility of salt. Right. So these are some of the very important, ideas in as far as some of these reactions that take place in an aqueous solution. Now, we'll take a short break for now, but after the break, we'll look more into detail into the solubility rules, because we've said clearly that there are some salts that are soluble in water, some are insoluble. So we'll try and discuss that further after the break. Let's take a short breather for now. Welcome back to our session. We're still discussing, the reactions that take place in aqueous solution. By now, we appreciate the fact that, an aqueous solution is that type of a solution in which water is the solvent. And remember, when we have a solution, we actually have got solid particles of a substance, dissolved in water completely to form what is called a homogeneous solution. Okay, so at the end of the day, we are appreciating the fact that these aqueous solutions in which water is, our solvent is actually a homogeneous mixture of some sort, right? So now we want to investigate and try and explore some of the, the reactions that take place within these aqueous solutions, right? Okay, so by now we are still talking about these solutions, and we are saying that in an aqueous solution, water is the solvent, and in a solution, what happens? We've got a solute and a solvent. Okay, so if the solute it dissolves completely in water, it gives us an aqueous solution. So now let's try and see some of these very important reactions wherein water is actually our solvent. Now, we are saying that substances that consist of polar molecules also dissolve in water. Right. Now, one of the things that we discussed in the previous segment is that when we talk about polarity of a substance or a molecule of a substance, it arises as a result of the difference in electronegativity. And what exactly is this electronegativity all about? It has to do with the tendency or the ability of an atom, of an element, to attract the bonding pair of electrons. So we used water as an example, and we appreciated that in the water molecule, the oxygen atom is actually, by comparison, having a greater electronegativity value compared to that of what? Of hydrogen. As a result of that, what happens? Any substance whose forces are in between them are weaker compared to the electrostatic forces that exist between water molecules, that substance will be completely soluble in water. That's why we are saying that polarity is a result of electronegativity difference that exists between particles of a substance. Right. Okay. So we're saying that these substances that consist of polar molecules also dissolves in water. So if a substance is molecular, it means it is actually covalent. Okay. Take note of that. So when we refer or describe the composition of a substance and we say it's molecular, we're saying that it consists of covalent bond, as is the case with water molecules. We've seen that before. So in this process, the molecules of the solute, this is the substance that actually dissolve in water, and the solvent form ions for the first time. So the process of ionization involves molecular or covalent substances. That's the main idea in as far as, dissolving of molecular substance in water. So the process involved there is ionization. Take note of that very important keyword. Right. Okay. Now let's look at a typical example. Okay. HCl is a molecular substance. Okay. If it is in a medium of water, so this is our solute, right? And then water is our solvent. Okay, that's our solvent. Okay, what happens is as a result of the strength of the electrostatic forces between the water molecules, we are able to detach these hydrogen ions from HCl, such that we get that hydronium ion and the chloride ion. Okay, this is ionization that we are talking about. Okay, so the hydrogen chloride molecule has a polar covalent bond. Okay, polar covalent bond, right? And chlorine is more electronegative. So what we are saying is, if we had HCl like this, okay, we would have something of this sort, right? Suppose this is the molecule of HCl. What we're saying is that because of the greater value of electronegativity, or that measure of the tendency of this chlorine atom to attract this bonding pair, or in this molecular substance, because this is a covalent bond, right? This will be slightly negative and that will be slightly positive. That's what we mean. So when we say that the hydrogen chloride molecule is polar and covalent, so the bond that exists between those two is such that they've shared a pair of electrons between those atoms so that they become stable. Okay. Now the chlorine atom is more electronegative, which gives us that type of polarity within that molecule. So the water molecules can attract the hydrogen ion to form the hydronium ion. And when we talk about the hydronium ion, we are talking about the H3O plus ion. Okay, right. So this is actually what happens if we to model this using particles. Let's say this is our molecule of HCl. As you can see, the chlorine atom is actually bigger than the hydrogen atom, and then this is slightly negative because of its greater electronegativity, while the hydrogen one is slightly positive. Hence, we say hydrogen chloride is a polar molecule. Okay, water is also polar, as we have discussed earlier. So what do we have here? We've got this hydrogen ion, okay, from the hydrogen chloride forming the hydronium ion, which is the H3O plus, okay, and then the chloride ion. So this is how the dissolving of a polar molecular substance actually takes place, okay? Right. Now, what are we saying? When solids dissolve in water, it can either be an ionic solute or a molecular solute. Now, let's talk about the difference between molecular and ionic. Okay, if it's molecular, it means it's a covalent substance. Okay, the bond that exists between the atoms that make up that element, it can be a diatomic element or it can be a compound, right? It's actually because of the sharing of electrons, hence it's molecular. So all molecular substances, they actually ionize. Okay, while all these ionic substances, they actually dissociate in water, in terms of them dissolving completely, right? So we are saying that ionic solutes, they dissociate, okay, while molecular one, they ionize. So molecular are covalent, right, substances. So take note of that as well. Right. Now we want to use examples to represent dissociation. Let's talk about magnesium nitrate as it dissolves in water. Right. Now, before we do that, I think the issue of chemical formula will always, every now and again, come back to haunt us. So we need to understand our periodic table fair and square. We need to be very clear about writing correct molecular formula or chemical formula of substances, because that is far-reaching implication in as far as what we'll do in terms of the balancing of the equation. So the issue of chemical formula, very, very important. It cannot be overemphasized. Right. So what are we saying here? If we have got magnesium is Mg, okay? It's a cation, which is a metal, right, of a metal, and then the nitrate ion, which is a polyatomic ion, is something like that. And then the formula of magnesium nitrate is going to be Mg, okay, and then 2 of the nitrate ions. So this is what magnesium nitrate formula looks like. So if this dissolves in water, what exactly is happening? We've got magnesium, which exists as solid at room temperature. Why? Because of the strong, electrostatic forces that exist between the magnesium and the nitrate ion. So this would be like more of a crystal lattice, right? So this would be like a crystal lattice. And then if it dissolves in water, which means the water then is the medium in which this process takes place, okay? But remember, this is this is what is going to happen. We'll have the magnesium ion surrounded by water molecules, as well as the nitrate ions surrounded by water molecules as well. Right. We can also talk about ammonia. Ammonia, the chemical formula NH3. It's also a molecular substance. And how does ammonia look like? We'll have N, okay, and 3 hydrogen atoms, right? So this is a molecular kind of a substance. Then what exactly happens if this ammonia dissolves completely in water? What happens is water, because water consists of the H plus and the OH minus ion, then we get the ammonium ion as well as the hydroxide ion. Right. This is how this reaction actually unfolds in as far as the ammonia dissolving in water. And this is actually ionization, because at the end of the day we get those two ions. So now it's the ammonia molecule actually accepting a hydrogen ion, then giving us the ammonium ion. So this is our ammonium ion. Okay. So this is an ammonium ion. Take note again of the chemical formula of it. Right. So these are some of the examples that have to do with ionization as well as dissociation. But I think with a lot of practice we can try and familiarize ourselves with this, because at the end of the day we need to be able to distinguish between ionization as well as dissociation, because these are some of the very important concepts that will have a lot of implication in terms of the chemistry, in terms of the types of reactions. So as far as these are concerned, these are some of the examples that we need to actually take into account. Welcome back to our session. We're still talking some of the reactions in aqueous solutions, but now we want to focus our attention on the solubility of some of these substances or these solutions, under different, conditions. That's what we want to look at now. Right. So now we'll look at the types of reactions that take place, but have to do with the solubility. We'll also take a turn and look at precipitation reaction and try to understand exactly how precipitation reactions actually occur, bearing in mind that some of the, substances are soluble and some are not. Right. Okay. Now, some of the terminology that will continue to quite, refer to a lot in our discussion are soluble. And if we're saying something is soluble, we're actually saying it has the ability to dissolve within a particular solvent. And then the opposite of that then becomes insoluble, right? So these are some of the key terms. Now, if we talk about a substance being an electrolyte, this substance must be ionic, all right? Electrolytes are actually ionic substances, right? Now, what's so special about these substances is that it has a lot to do with the property of electrical conductivity. So, in essence, an electrolyte is actually a solution with a high concentration of ions. So it's actually an ionic solution that actually conduct electricity. So it means that if we have a solution that we describe as an electrolyte, it simply means that electric charge or electricity can pass through that solution. Why? Because there are free moving ions in that solution. Hence we are saying that all electrolytes are actually ionic substances, right? That's a very, very important chemical property of ionic substances. And then now let's look at solubility and conductivity, right? Conductivity is, in this case, we're talking about electrical conductivity, right? We are talking about electrical conductivity. So a solution that has got high conductivity is formed by soluble salts, and these salts are actually ionic substances. Right? So there's a strong link between chemical composition, solubility, as well as conductivity of a given substance. Right? And then also the solubility rules, which is very, very important. We are saying that all salts, all, it means, you can list them from group 1, you've got your lithium, you've got your sodium, you've got your potassium. These are group 1 metals, and ammonia are all soluble. So any salt that is based or is made up from a group 1 metal is actually soluble. Okay, that's solubility rule number 1, right? And then also, all nitrates are actually soluble. So we're talking about what? Potassium nitrate as an example. Okay, it's very soluble. All right, as long as it's a nitrate. We can also talk about magnesium nitrate for argument's sake, because we are saying all nitrates are actually soluble. Okay, so take note, as long as the salt is a nitrate, it is completely soluble, right? Okay, and then again, in as far as the solubility rules, we are saying all, take note of all, halides are soluble except for silver, lead, and mercury. And when we talk of halides, this draws our attention to our very, very important tool, which is the periodic table of elements. What elements do we refer to as halides? Okay, maybe that's the big question that we need to actually ask ourselves. So if a substance is a halide, it means it's an element that occurs in group 7. So all group 7 elements are actually halides. What are halides? Examples are your fluorine, chlorine, okay, bromine, as well as iodine. These are halides, which are in group 7. So there is something special about group 7 in terms of chemical properties, okay, which appeals also to the solubility of these substances. Okay, so if we are talking about all halides, we're talking about these substances, except in silver. If it's a silver halide, we can talk about silver chloride, okay, for argument's sake. Okay, chemical formula, very important. We can talk about silver bromide, all right? We can talk about silver iodide. It means these are actually insoluble because we are saying these are actually exceptions, right? Okay, and then again, all sulfates are soluble except for barium. So sulfates are these salts that contain, the sulfate, polyatomic ion. So if we're saying barium sulfate for argument's sake, okay, barium sulfate as a salt, this is insoluble. All sulfates are insoluble except barium, lead, and mercury. So the sulfates of barium, lead, and mercury are actually insoluble. Hence, we are saying that these are our exceptions, right? Okay, and then now let's look at the carbonates, right? And the moment we start to say carbonate, we need to draw our attention again to chemical formula because it will play a very important role in as far as us understanding or predicting whether these substances are soluble or not, now that our focus is on solubility of salts, right? So chemical formula, we cannot overemphasize the importance of that. It's very, very important that we understand the chemical formula. So all carbonates are insoluble except the carbonates for group 1 metals and ammonia. Okay, they are insoluble. So if we have, let's say for argument's sake, sodium carbonate, okay, the carbonate ion is CO3, 2-, okay, and then let's say, for example, we've got sodium, which is group 1. Now, if we're saying all carbonates are insoluble except group 1 metal carbonates. So a metal or carbonate of a group 1 can be sodium carbonate for argument's sake. So the formula becomes NaCO3, okay, then we need 2 of those because that's 2 negative. Then this is actually soluble. So this is as far as the solubility of these particular substances is concerned. So before we do any reactions, we also need to take into account the solubility rules as we have discussed them. So in as far as solubility rules, is either we know them or we don't. But our understanding of these solubility rules will actually help us to predict in as far as these reactions that take place in aqueous solutions are concerned. Then we're able to say, okay, as long as it's a metal from group 1 and it forms a carbonate, is that carbonate soluble or insoluble. For us to actually arrive at a conclusion, we need to understand the solubility rules. And also, the issue of chemical formula is very, very important. We cannot overemphasize on that. Now, when we talk of precipitation reactions, when we have two solutions of soluble salts which are mixed together, they form an insoluble salt, and that settles at the bottom of the container, and then it forms what we call a precipitate. So when a precipitate is formed, that type of reaction is referred to as a precipitation reaction, right? So a reaction that produces a solid which is insoluble is called a precipitation reaction. So in precipitation reactions, rather, we are looking at also applying these solubility rules, right? Okay, let's look at an example here. Barium chloride and silver nitrate are mixed together, okay? We've got barium chlorides, these are salts. Silver nitrate and barium chlorides are salt. What do we get? We get silver chloride and barium nitrate, okay? Now, what happens here? This is a precipitation reaction. And how do we represent a precipitation reaction? We would have something like this. We know that, a halide of silver is insoluble. So this will be solid, and then the color of this precipitate is what is going to tell us which halide is involved. So this is a typical example of a precipitation reaction, and the reaction has already been balanced. But for us to balance the equation of reaction, we need to have the correct chemical formulae, right? Which is very, very important. Welcome back to our segment. We're still looking at reactions that take place in aqueous solution, but now we want to, try and apply these solubility rules in terms of, testing for, some of the very important substances. It could be your halides, it could be your sulfate, it could be your carbon. But bear in mind that our understanding of the solubility rules are very important, in this case, right? So we'll look at, the precipitation reactions, okay, as far as solubility is concerned, and also it has a lot to do with some of the, gas-forming reactions that we would want to also try and focus our attention on, right? So now, if we are testing for the presence of an anion in a solution, right, what is it that we mean when we talk about an anion? These are negative ions, okay? These are negative ions. So if an ion is negative, we would refer to it as an anion, right? For argument's sake, we can talk about a carbonate, okay, as an anion, okay? We can talk about a sulfate as an ion, okay? So these are typical examples. So precipitation reaction, okay, gives us a way to kind of understand or identify, which ions are present in an aqueous solution, right? Okay, and then using the precipitation reaction to identify anions, let's say we are testing for halides as an example, and the halides in this case could be your chloride ion. It is still an anion because it's negative, okay? It is a negative charge. It could be a bromide. Also, it may be an iodide, all right? These are halides which are group 7, right? So suppose we've got a sample of an unknown solution, and what is of interest to us is to understand which ions of the halide are present. Could it be the chloride? Could it be the bromide or the iodide? So what do? We add silver nitrate. Silver nitrate is AgNO3, right? So this is an aqueous solution of silver nitrate. We add it to this unknown sample. Then if there is a precipitate formed, then we can go on and decide based on the color. But if there is no precipitate formed, then what happens? What are we saying? If there is no precipitate, if adding to this unknown solution, so if we have got this unknown solution, whatever, let's say it's X, and then we add silver nitrate. we add silver nitrate, and then we know that there is no precipitate, okay? Then we know that there is no carbonate or no halide in that particular sample of the unknown solution. But what about if there is a precipitate, okay? And if we add nitric acid to this precipitate, what happens? we know that there's either a carbonate or a sulfate, right? Okay, because that's what it means. So if we add nitric acid and the precipitate remains, two things may happen if we add nitric acid. Nitric acid, HNO3, it's a strong acid, right? Okay, so if we add it, it's either a precipitate will not dissolve or a precipitate will dissolve. If the precipitate dissolve, then it means what is present is actually a carbonate, right? All right, this is what we mean. So the unknown sample, we add silver nitrate, no precipitate, we know that there is no carbonate, there is no halide. And then if a precipitate forms and we add nitric acid to it, we know that if the precipitate remains, it's something else. But if we're adding nitric acid to it, it actually dissolves this precipitate, then we can say, yes, indeed, it is a carbonate that is present, right? Okay, and then if the precipitate remains, because its halides are insoluble, then we know it's one of the halides that are present. So this flow chart kind of helps us to understand the bigger picture in as far as testing for these N ions. So N ions could be carbonate, sulfates, it could be the halides, right? These are of interest to us. Now, testing for the presence of a halide, ions in a solution that is given. Obviously, this solution is unknown in terms of its composition. So the color of these silver halides are very important. Now, if the silver halide is formed, the color will be white. So the silver halide concerned there it's a chloride. Then it's going to be Ag, Cl. So this is a precipitate, right? Then which is solid. And remember, to represent a precipitate in a reaction, we'll draw that symbol to show that it's a solid substance that is actually insoluble, right? But then if it's cream, it's obviously silver bromide. So then silver bromide is AgBr. It's another solid, and then a precipitate that is formed. What about if it's an iodide, right? The iodide, which is yellow in color, would have AgI, which is a solid precipitate as well, right? Okay, now if we want to test for the presence of sulfate ions, okay, which is another N ion, what do? We add barium nitrate. So for test for sulfate, it's barium nitrate that is used, solution that is used, right? Take note of the chemical formula of barium nitrate, because if we are going to write a balanced equation of reaction, that becomes very, very important. So if the precipitate forms and then we add nitric acid, the precipitate dissolves, it is a carbonate ion because the carbonate is soluble. So barium carbonate dissolves completely in nitric acid, while the sulfate does not. So if a white precipitate remains, the sulfate ions are present. What is important in this case is to realize that whenever it's a white precipitate, two things may be possible. It could either be a carbonate or a sulfate. But then to determine whether it's a carbonate or a sulfate, if we add nitric acid solution to this precipitate and it dissolves, then it gives us, it already indicates that this is a carbonate. But then if it doesn't dissolve, it means it is a sulfate. So that comparison, that distinction becomes very important, right? Okay. And then here's a simple question just to apply this understanding or this knowledge. We've got 3 beakers labeled A, B, and C. They contain solution of sodium salts, okay? These are salts whose composition is unknown, but we know that the metal present is sodium. They also contain either a halide ion, a sulfate ion, or a carbonate. So it's either a halide, a sulfate, or a carbonate, right? Now, these are the clues. No precipitate remained in beaker A after testing for halide and sulfate ions, okay? So there was no precipitate that was formed. These are some of the clues. Identify which ions are present in each beaker based on the following. If there is no precipitate in the beaker A after testing for halide, it means there are no halides or sulfate ions in beaker A, right? A yellow precipitate formed, okay? Let's take note. Yellow precipitate formed in beaker B after testing for halide ions. We know the one that has got, that color in terms of, the halide, and we used silver nitrate, right? And then a white precipitate formed in beaker C after adding barium nitrate and remains and it remains after adding the acid. So if we can go back, the yellow precipitate in beaker B is such that, if we say silver nitrate, okay, plus the yellow precipitate is a sodium salt, okay, it's sodium bromide, okay, iodide, because it's yellow, okay, iodide, sodium iodide, okay, which is an aqueous solution, okay. What was formed here is silver iodide, right, which is a solid, right, plus sodium nitrate, right, sodium nitrate, okay. So the precipitate, this is the yellow precipitate that was formed, okay. So the halide that's present in B is actually the iodide one, okay. So we can immediately, so if we were to write down the precipitation reaction ionic, we would have silver ion, okay, in aqueous solution, because these are reactions that take place in aqueous solution, plus the iodide, okay, which is in solution. It gives us that precipitate, okay, which is that color. Okay, so that's the precipitation reaction that occurs there, right? Then a white precipitate formed in beaker C after adding barium nitrate and remains after adding the acid. So this definitely, if it's not soluble, if it remains, it means what was present there is actually, if we add, because it's a sodium salt, we can immediately predict that it's a sulfate, right? So if it's a sulfate, we have got that, okay, that's the salt, okay, plus we added barium nitrate to it, okay, barium nitrate, okay, aqueous, okay. What did it give us? It gave us barium sulfate, right, BaSO4, okay, solid, okay, which is the precipitate here. That's white in color, okay, plus what did we have here? We also have sodium nitrate as the other substance, right? But also take note of the chemical formulae, right? So if we add nitric acid to this and it doesn't dissolve, then it tells us that it is the sulfate that was actually formed, right? Okay, so in as far as, but the reactions, we need to understand how we test for each of those anions, which is very, very important. But also bear in mind that if this was a carbonate, what would have happened? One may ask. Let's say if it was a carbonate, then we know that if we added the acid, and the acid that we're talking about here is nitric acid, right? It's nitric acid, which is a strong acid, right? So if we say, so for argument's sake, it was barium carbonate, okay? Okay, it was barium carbonate, okay? And then plus this is precipitate plus HNO3, all right? Aqueous. This is actually a gas-forming reaction, right? It will form it will give us a salt and carbon dioxide and water. So the salt that will be formed will be barium nitrate and carbon dioxide. sorry, barium nitrate, right? NO3. To take note of the formula, plus carbon dioxide gas, right? So take note of the symbol there. That's my, and then also water will be the other product that will be formed in this reaction. So this is how we distinguish between a sulfate and a carbonate. So if it was a carbonate, it was going to be a white precipitate which dissolves after adding the acid, which is nitric acid. Okay, so these are some of the tests that you actually do, but of particular interest to us, again, beyond just knowing or, predicting, we also need to be able to write the correct equations for each of those precipitation reactions. And a lot of practice will actually go a long way in us understanding some of these very important concepts. Okay, that's the time we had for today. Just do as much practice as you possibly can on these equations. Otherwise, for myself, Themba Ncube, it's bye for now.